Okay, today we're going to be talking about using the Hardy-Weinberg equation to solve some problems. First, let's just quickly review what the Hardy-Weinberg equation is. Basically, we have two variables, little p and little q. P plus q add up to 1. P is the variable for all dominant alleles. It is also known as the dominant allele frequency. It will be written as a decimal. Q is all recessive alleles. It is the recessive allele frequency. It will be written as the decimal. Because dominant alleles plus recessive alleles includes all of the alleles that there are, P plus Q adds up to 1.0. We can also look at the different genotype frequencies using these same variables. We use a slightly different form of the equation. This is p squared plus 2pq plus q squared equals 1.0, where p squared is homozygous dominant, 2pq is heterozygous, 1 dominant, 1 recessive, and q squared is homozygous recessive, 2 recessive alleles. All of these would be given as decimals, and these are the only 3 possibilities, so when you add them up, it will become 1.0. This information does come from a Punnett square. So if you look at a Punnett square, you can see the source of the Hardy-Weinberg equation. Here's a Punnett square using P for capital A, the dominant allele, and Q for little a, the recessive allele. Notice that you would end up with 1 big A, 2 big A, and 1 little a. This then can be translated into P's and Q's. So the big A becomes P squared, the big A becomes PQ, and the little a becomes Q squared. Notice this equation comes then from the Punnett square. The Hardy-Weinberg equation can be used to show if allele frequencies are changing from one generation to the next. So you can calculate allele frequencies for generation 1, calculate allele frequencies for generation 2. If they are different, then we can assume that evolution has occurred. If instead the proportion of genotypes remains the same, then the population is not evolving. Remember that the Hardy-Weinberg equilibrium is an ideal state. That means that it does not exist in nature. That's because in order for Hardy-Weinberg equilibrium to be occurring, many conditions must be met. The population must be large, there must be random mating, no migration, no genetic drift, no mutation, and no natural selection. Pretty much, it's impossible for all of those conditions to be met. So, Hardy-Weinberg equilibrium is an ideal state. It does not exist in nature. Let's go ahead and take a look at solving some problems with the Hardy-Weinberg equation. Let's consider a population where 9 out of 100 people have a recessive trait for short fingers. In this problem, we first want to find the allele frequencies. What that means is we want to find P and Q. Allele frequencies correspond to P and Q. When we are finding allele frequencies, we always want to find Q first. That is the easier one to find. You should always start with Q. Q stands for the recessive trait. In this case, short fingers is the recessive trait. We're just going to go ahead and call that little d. And in this problem, we know that little d is present 9 out of 100 times. So we know that little d, which is the same as q squared, is 0.09. Now, how did we find that? We know that it is 9 over 100. It comes from this part of the equation right here. So when we calculate that out, we know it's 0.09. That is q squared. Now, we haven't yet found q. In order to find q, we need to do one more step. Q equals the square root of q squared. So we need to take the square root of 0.09, and that is how we get 0.3. So Q is 0.3. Once we have found Q, we can now find P. We're going to use this equation. P equals 1.0 minus Q. So we're going to plug in Q, and we will get P value of 0.7. So we now have a Q value and a P value. This answers what are the allele frequencies. Now, another step in this problem might then ask you to take the P and Q values and find the different genotypes. So now they're going to say calculate the proportion of people in the first generation with each genotype if the Hardy-Weinberg conditions are met. So we know that our P was 0.7 and our Q was 0.3. One genotype is capital D, homozygous dominant. That would be P squared. So we just need to take the P value, 0.7, and square it. So big D would be 0.49, or written in percentages, 49%. Here's a picture of what this trait actually looks like, normal fingers. For heterozygous, big D, little d, that's 2PQ. So we're just going to take 2 times the number for P, 0.3, times the number for Q, or 0.3 is actually Q, and 0.7 is P, but we're just going to plug those two values in, multiply them together, we get 0.42, which is 42%. Again, normal fingers. Little d is Q squared. That would be short fingers. We're just going to take the value for Q, 0.3, square it, and get 0.09, or 9%. Here's an image of what that individual would look like. So this is another type of problem you can do. A third type of question they might ask would be then to say, how many people would be heterozygous if the population had 650 people? So now they're asking you to consider a specific population size. So we know that our big D, little d, which is our heterozygous, was 42%. And we then want to calculate what 42% of 650 is. So we would take 42% times 650, and in this particular situation, 273 people out of our population of 650 would be heterozygous. Here is another representation of this same data, kind of showing you a visual idea of how these numbers came to be and corresponding it to the Punnett square. Take some time to look at this if you're interested in how it fits together with the Punnett square. This is, again, the same information that we just did, simply written out in a different form. If you're interested, pause the video and make sure you understand this diagram. Two quick things to remind you of before we go. First, frequencies will not change from one condition to the next if the Hardy-Weinberg conditions are met. Basically, conditions will not change from one generation to the next if there is no evolution. So if the conditions are met, if the frequencies are staying the same, we would then conclude that no evolution is occurring. However, if the frequencies do indeed change, that is how we can prove that evolution has occurred.